So the basic point is that you need to have a waveform which has a small wavelength, right? So you want to increase the resolution. Why do you want to increase the resolution? Because you want to increase the magnification. So a light source, the visible light source, has its own limitation at maximum magnification or resolution that it can reach. After that, even if you keep on magnifying, there will be an empty magnification because you will not be able to resolve the points, right? So that is why electrons are required to have increased magnification and resolution. So that is what is a transmission electron microscope that we'll be talking about today. So anybody can identify? You're looking at this. Okay, I'll tell you, this is from a lung. This is a pneumocyte, cells which line the alveolar space. Those can be seen by a light microscope. So why I'm showing you this electron microscope picture. Something which was causing havoc in your life for the past 2.5 years. COVID. So virus particles, can you look at them in the light microscope? No. So what do you require? So where are these? So you see these beautiful viral particles, right? You can see them here also. So if you even have a high resolution, a better microscope, you can even look at those spikes, the corona spikes. That is why it is known as a coronavirus. So these are the virus particles. So this is the cilia, right? But these are the particles which you can see. This is nothing but these are proteins, surfactant proteins which are there in the cytoplasm of the human cell. Okay, that can be seen by an electron microscope, but that is not why I'm showing you this electron microscope. Okay, so that is the importance of an electron microscope. So this is about COVID-19. So a COVID-19 particle is how big? Around 80 nanometers, but different papers have talked about it as 50 to 100 nanometers. Okay, this is just to give you a feel of what is the size difference for different cells so that you understand what we are looking at. So when we talk of a mammalian cell, so this is a neutrophil. So we can say it is around 10 microns. Okay. And a normal human cell will be around, apart from us, this is also a cell, but apart from the neutrophil, eosinophil, human cell is looking at of course, it will vary about the type of cell we are talking about, but it will be something around 80 to 100 micron large. A normal tissue cell, not talking of the blood cell. A bacteria is around 1 micron. So what can I showed you a virus particle, right? So this is what an electron microscope can do. It can show you particles which are very small. So we can look at ribosomes under the transmission electron microscope. We can, what is the size of the mitochondria? I know you will not remember that. It is around, bacteria can be seen by a light microscope also, isn't it? If you look at the size of a mitochondria, it is around 0.5 to 1 micron. So practically speaking, you should be able to look at a mitochondria in a light microscope, isn't it? But if you see a cell, you can see those granules which represent the mitochondria, but the internal structure cannot be seen under a light microscope. That can be seen only by an electron microscope because you need to resolve the different parts of the mitochondria to say that this is a mitochondria. Okay, so that is why the electron microscope is important. So this is just to give you an idea. So what we are talking about is sub-microscopic particles or things that can be seen only by an electron microscope. This is just to show a gradation that you have a microscopic picture, light microscopy, scanning, and the transmission. So coming back to the human cell, as I said earlier, so you remember this from your biology days, 11th, 12th, right? So this is a typical cell. And that is, as pathologists, we are able to look at it each day under the electron microscope. And this is how it looks when we look at it. This is a hepatocyte, liver cell. This is how it will look under an electron microscope. So now you can make out these are the mitochondria, right? And these are, what are these? This is not Golgi, this is endoplasmic reticulum. And depending upon whether you are able to see, I'm not sure if you are able to see, but I can see these particles. You can see these small particles on that. So it is a rough endoplasmic reticulum. So you are able to see these ribosomes also in the electron. So that is why an electron microscope is required, and that can, some things cannot be achieved by a routine light microscope. Now you see the size difference between a light microscope. You can keep it on the desk and look at it. An electron microscope, the transmission electron microscope requires the whole room for itself. It takes the whole space. I will talk about it, why it needs so much of space. But it needs the whole room to keep the electron up. So that is the size difference between a light microscope and a transmission electron microscope. The first electron microscope was built in around 1931. So it is relatively recent. Okay. And with a resolution of 50 to 100 nanometers. And Dr. Ruska, who got a Nobel Prize later for this discovery, he had tried to make a electron microscope. And this is the earliest model of an electron microscope which was used. And this is his initial writing in which he designed an electron microscope. And he said that it was initially capable of only 16,000 magnification. A routine light microscope gives you how much of magnification? 100x is the oil immersion. When you have the IP, 1,000. And if you replace the IP by 10x by a 15x, it can even be 1,500. But most of them, if you use an oil immersion, it will be 1,000. Right? So this was that. The initial one showed you 16,000 magnification. Okay. And then companies started coming in, private companies, to make these electron microscopes. So if you can see that it is relatively new, it is 1973, right? That electron microscopy started. So this we have been talking day in and day from the past 2 days. So what is important for an electron microscope is the resolving power. It can differentiate 2 points, 0.2 nanometers apart, and a light microscope can do it for 0.2 microns, and your eye can do it for 0.2 millimeters. Okay. So this is the crux of it. Lambda, that is what we're talking about. If lambda is small, the distance between the 2 points which can be resolved becomes small, and therefore the resolving power increases. Right? So that is why the scientists thought that because electrons have a very short wavelength, they can be used as a light source to increase the magnification and the resolving power. So the beauty about the electrons is that the resolving power in an electron microscope also depends upon the accelerating voltage. So what I'm trying to say is that according to the accelerating voltage with which the electrons pass, you can increase the resolving power because the wavelength keeps on decreasing. Okay, so for example, in our microscope, we have a microscope which is we can use it up to 200 kV. So, but 120 kV. So we have 80, 100, and 120 kV. So when we use an accelerating voltage of 100 kV, the wavelength decreases further, and therefore we can go to higher magnification. So that is why the accelerating voltage is important. And the other thing is that the lens that we use in a light microscope is which type of lens? What is it made up of? What are your specs made up of? You have different glass lenses in your microscope. Whereas electron beam cannot pass through the glass, right? So it needs electromagnetic lens. So that is how it is different from a routine light microscope. These are the basic differences between a light and an electron microscope. So what the source of illumination is electrons. You have, so if you see, I have mentioned the kV. So at 100 kV, this is the wavelength. But if I decrease the kV, the wavelength also increases and vice versa. The medium electrons can travel in air. Air? They can travel, but they will command all particles which are there in the air. The these are not there. So they need a vacuum system. And that is the reason, because of the accelerating voltage that you require, and because they can only travel in vacuum, you have such a big instrument that is used for an electron microscope. And lenses, as I said, is electromagnetic. Screen that we see is a fluorescent screen. I'll show you in one of the figures. So when the light beam strikes the screen, it fluoresces, and therefore you can look at it. So there are basically two types of electron microscope. One is a scanning and one is a transmission. What I will be talking about today is transmission. Professor Mitra from CDRI will be talking about scanning electron microscope. What is the difference? Can anybody tell me? Any gastroenterologist here? Any medicine person? Anyone can tell me what is this image is what from which microscope? If you want to see the surface of the topography, you do the scan. Which figure is scan? Left side scan. Left side, below scan. That the line of there. The small is the small. Okay. So that is a light microscopy picture. This is a scanning electron microscopy picture. This is a transmission electron. Now you understand the differences. So the scanning just looks at the topography. So what we'll do is we'll take a section of the tissue and just keep it on the holder, and we can look at it in the scanning electron microscope, just like this. So what we are trying to see is the surface. But when we are looking at the transmission electron microscope, we will embed this tissue, cut section, and then see that is a transmission. Why is it known as transmission? Because the image is formed by the transmission of the electron. In scanning, yes, you can see that is you have an actual picture on the photography where you can look at the 3D surface. Absolutely. I'll come to that, but most of the IITs in India, because they deal with a lot of material science, have these high-end microscopes which look at these structural, and they are 3D constructions. Okay, now again, which one is scanning and which one is transmission? Just to tell you the concept. So that is an RBC, this is a bacteria, that is a mitochondria, and that is a glomerular basement membrane. Okay. These are three elements. This is a, what is this? And what is this? These are platelets, right? So this is how it will look. That is an RBC, a neutrophil, or and a platelet will look under a scanning electron microscope, right? And this is how a bacteria will look like. So it is quite a fascinating science. So now I'll be talking just about transmission electron microscope because scanning will be taken up by Dr. Mitra. So as I said, it is a direct counterpart and it involves a passage of high velocity electron beam, and it is known as transmission because the specimen should be thin enough that around 50% of the electrons are transmitted. And that is why you will get an image. Otherwise, you will not get any image of the tissue that you have put in the electron beam. And the emergent beam is focused by a set of lenses which are electromagnetic lenses. So when we look at the transmission electron microscope, these are the components. This is a microscope column. You have surrounding it a large vacuum system which is made up of different pressure pumps. which maintain the vacuum, and then you have the control panel. There is a power supply unit which is separate. This is the at the back you have the power supply. Air compressor is also needed and water chiller is also needed because the electromagnetic lenses become very heated up, right? And so they have to be cooled. So that is why a transmission electron microscope is a big instrument which requires a large amount of material to make it functional. So when we look at the cross section of the microscope column, so the electron gun is at the top. So there is a beam which comes from the electron gun. So electron gun is also made up of, you can use different type of filaments, but we also use the tungsten filament. Other filament which is used is known as the lithium bromide, that is LaB6. So it emits an electron beam, and there is an anode which so that the electron beam has a coherent path. Then you have the condenser lens, a specimen chamber where the specimen is kept, and different sets of lenses. And lastly, you have the viewing chamber. So we have an illumination system that is of electron gun and the condenser lens, the imaging system. And this is what is an electron beam which comes from the tungsten filament, which acts as a cathode. And this is the anode, so that the beam is effective, electron source is maintained. These are the electromagnetic lenses which are used. So when we go to the image translating system, it has a fluorescent screen. As I said earlier, the electron beam comes from after passing through different lenses through the specimen, and then it comes on the fluorescent screen where an image is formed. And now you have the CCTV cameras and the digital output where you can look at it on the digital screen. Initially, we used to keep photographic films. In the earlier microscope, there used to be photographic films which used to take those images. So this is how a fluorescent screen looks like. So if you look at this image, this is an image of what? What is the tissue which has been kept in the specimen sample? So, give me the part. What is the part? Glomerulus. Very good. So these are the foot processes. This is the glomerular basement membrane, and these are the capillaries of the capillary lumen of the glomerulus, right? So these are glomerular capillary loops, right? And this is a podocyte, which is sending its processes towards the glomerular basement membrane. Okay, this is again to show it in a different way, but similarly, you have lenses and a source, and the imaging system is at the bottom. So the image formation in light microscopy is by differential absorption, whereas in electron microscopy, it is by the transmitted electrons and also by the electrons which are scattered. So the electron scattering power is increased by solutions which have high atomic weight. And therefore, the staining that we do in a light microscopy is completely different from what we do in an electron microscope for tissue which has to be seen by an electron microscope. So what do we need to have a tissue which can be processed for electron microscopy? What do you think? How do you take tissue for light microscopy? So you've done a surgery or someone has done a biopsy. Where do you keep it? And send it to the pathology lab? What do you think happens to it after that? Sectioning before processing. Section. So you already there in the formula. Go through a lot of processing steps. One of them. And then it is embedded in what? The tissue is embedded in paraffin. It is embedded in paraffin, and then you cut sections and look at. Remove the paraffin, of course, by methods, and then you stain it and look under the light microscope. So it is paraffin embedded. So that is known as formalin fixed paraffin embedded. That is FFPE. But can we use the same procedure for electron microscope? Why? The heat generated by the electron microscope is too much. Heat in the bottom. Electron beam itself has to be. So, what will happen to the vat? Right? Then it is remaining. For light microscopy, for dehydration is done, but still you have some amount of water mixture. But when you do it for electron microscope, you cannot have any amount of water in the tissue. Okay, so that is why the processing for electron microscopy is different from what we do for a light microscope, right? So, and basically you want to at the same time preserve the ultrastructure. You want to remove the molecule, water molecule, but still you want to preserve the ultrastructure, and that is why the processing for TEM is cumbersome. It is time taking, it is cumbersome, and there is a lot of technique which is involved. Technical aspect is very important for processing on electron microscopy tissues. So the aim of specimen preparation is that the ultrastructure should be preserved. The section should be thin because, as I said, 50% of the electrons should be transmitted. Embedding should be in a material which can withstand the electron beam. And we need to stain with high atomic metal because we not want it to be scattered also, transmitted and scattered at the same time. So that is why we need to take into account these things when we process for transmission, and that is why it takes time as compared to a light microscope. So what is the fixative that we use for electron microscopy? Why not founded? Okay, so basic sense that it keeps the ultrastructure preserved, right? But when you take it in glutaldehyde, we keep the tissue in refrigerator as compared to a light microscopy where we never keep the tissue in refrigerator. We have to keep it at room temperature. Why? Because the penetration power of glutaldehyde is very low. So if you keep it outside, the tissue will get photolyzed. So that is why we take it in glutaldehyde, and if you do not send to the lab immediately, you are asked to keep it in your door of the fridge. Okay. So as I said, fixation is by glutaldehyde. You also need a second fixation, that is by osmium tetroxide, and the steps are almost similar as you have for light microscopy. Resin are used for it. As I said, what were you using for light microscopy? Resin. And then you embed, polymerize. These are the steps. So just to compare, this is how a block of a electron microscopy looks like, and this is how a block for histology looks like. This is a wax block. Look at the amount of tissue that you have in the wax block. This is the tissue for, where is the tissue? Can you identify? You see something black at the tip? That is the tissue. This is the amount of tissue that you can process for electron microscopy. I'll show you the grid on which we keep the section. So that is why you need special technique for processing, and you need special techniques for cutting and staining for these small amount of tissues. And still we are able to give a lot of information from the electron microscope. Okay, so that is why it is said that it needs an ultra microtome, because the tissue is so small and you need very thin section. How much thin? 60 nanometers, around 60 nanometers. So that is the thinning, and we do staining with uranyl acetate and lead citrate. This is the grid, right? You can see this, just a small copper grid where we keep the section. It is around 3 millimeters in diameter. That is all. Of course, electron microscopy, because we are using material that is resin, osmium tetroxide, uranyl acetate, lead citrate. So this is all hazardous material, and therefore we need to take into account a lot of precautions when we are in an electron microscopy laboratory. So now, what are the other procedures an EM can do? Do we have somebody from microbiology? What is negative staining? What is negative staining? So your background is stained, but your thing of interest remains unstained. So that is known as negative staining, and that we can use for virus particles in electron microscopy. And so it cannot even just used for tissue sections, it can also be used for viral particles, particulate material. It can be stayed like a negative state. And of course, we also, if you have some nephrology residents, you will be knowing that we also take out tissue from the paraffin embedded tissue, and then you can process it for electron microscopy. We can do immunoelectron. There are methods like cryofixation, which may be of interest to PhD students, where we can cryofix the tissue so that the water becomes ice and complete ultrastructure is maintained. Okay, so this is about the negative staining for a virus particle. What are the limitations? The limitations appear to be obvious. So it is a very expensive instrument. What do you think would be an average cost of an electron microscope? A basic microscope. What is that a light microscope? $1 lakh approx. Okay, depending of course on the type of lenses and a lot of. What do you think would an electron microscope cost? Depends again on the type of microscope, but a basic one will not be less than 2.5 or 2.5, 2.5. A basic one, I'm talking about. The ones that the IITs have would be something quite high, depending upon how much they can resolve. So the other thing is it is expensive. Yes, it is time consuming. A smaller area, of course, is examined. Vacuum is essential. There is an electrical and optical systems which are required. The sample cannot be volatile. It cannot be wet. The processing is so technique dependent. And of course, as I said, because you use a lot of hazardous chemicals, it can be a health hazard if you do not work properly in an electron microscope laboratory. What are the applications? That you will tell. Who's from nephrology? No, I think everybody can tell. What do you think? If that is something, why do you need it in nephrology? That is one science that we are using the maximum amount of electron microscopy for nephrology. That is why I'm asking for nephrology. So what do you use it for? Right. Good. Good. One is the location of the deposit. Second is the type of deposit. You heard about organized deposits? Not only the location, but the type also. Right? Yes. And then you said about photosynthesis. Right. So when you have something with anything else, somebody wants. Right. So that is organized deposit. That is known as organized deposit. So nowadays, if you look at the practical medicine part of it, most of the applications are in for diagnostic field is in nephrology, and the other area is sometimes in liver, but not so much important. Rarely in liver, one or two indications. Other would be skin, muscle, skin and muscle, because you want to look at those adherent junctions between the keratinocytes, between the collagen. But that also is now relatively less used because you have different immunohistochemical markers and other techniques which can help you in making the diagnosis. So basically it is for renal diseases, Alports, thin basement membrane, you're looking photocytopathies, inclusions, organized deposits. Histiocytosis, initially it was used, but now you have, because of the immunohistochemical markers, it is not mandatory. Similarly for skin disorders, myopathies, neurological diseases. Some of the neurological diseases can be diagnosed only by an electron microscope. Some like CADASIL, NCD, and NCL. For cilia, it is still being used to look at these dynein arms. You remember your biology classes, these were the. So you can look at cilia. So especially in respiratory ciliary dysfunction and even in patients with infertility, where you want to look at the motility of the sperms. These are some examples of mitochondrial myopathy. This is of a CADASIL, where you can see these inclusions. This is Alports, where the basement membrane, you can look at it, and it is a basket weave or splitting of the glomerular basement membrane, the lamina tensor. So there are a large number of models of both of scanning and transmission electron microscope, and they keep on improving day by day because of the material science applications. For IT and engineering techniques, you need these instruments for the material sciences, for structural biology, for cellular biology, and various biomaterials. This is something which fascinates a lot of people, so that is why I put in the pictures. Nanoparticles. So these are very small particles which can be looked by an electron microscope. And the size is around, it varies from 1 to 100 nanometers, and therefore you have this bar. Okay, so biomaterial things. This is about something like we keep on having students from the universities who keep coming for visualizing electron, and this is our electron microscope. This is a column. And this is our team in electron microscopy, our technician, Madhulika, Farat, all some of my peers. Okay, any questions? How long do we? So I believe you can keep it for 2 to 3 minutes, but as I said, you have to keep it in place. Second, you have to cut it into small pieces. It should not be more than 1 inch. So, for example, a renal biopsy comes to us, we generally, as soon as it comes to us, we cut it into small bits that are not more than 1 millimeter in size and keep it in the refrigerator. You can keep it for longer, but you have to remember that it is in the refrigerator. But ideally, if you have a lab which is working nearby, it is better to process it, osmicate it, and then keep it in buffer. So that is what we do. So if, for example, we have a tissue which is very large. We know that we will not be able to make so many counts. So we take the tissue of interest and rest of the tissue, then keep it in nucleotides, but we can also process it in buffer. And that again, because it is already osmicated, it does not exist. It is fixed, osmicated. Any other question? What happens with the membrane of the mitochondria and the crispy? So we want to look at finer details. So you have to be very, very particular that your nucleotide photosynthesis, osmolality, very perfect. So that there is more degradation of the. As compared to neurons, still you will be able to look at the organelle. But if you want to go into the high power and look at each organelle separately, then of course you have to take into account that everything starting to the end is very perfect. Otherwise, you will not be able to see those double membranes. That is only. Otherwise, processing is almost finished, except when you are doing immunometry. Okay. Then somebody check if you have a specimen, otherwise. Can you speak louder? No, it is not radiation. It is basically fumes. And so the allergic to the thing that we are using granular sulfate. So when we dispose them, and we have to inactivate them. For us, we use the charcoal and then inactivate and take it together, and then it goes incinerator at one time. So that is a like I am very allergic to the resin. So if it comes into contact with skin, that will get out. So that is why it has its own effect. That is how it is. But yes, people have been trying for different alternatives, like for uranyl acetate and especially uranyl. You know, uranyl acetate will be with others, but still they have not been able to find a good alternative. You wanted to ask something? What's your name? So you will have to read out the paper and see at what stage you want to erect what. That is how I understand. Where the autofocus function has happened, right? So you can do that. You understand the experiment, but you for example, if you want to erect it as the CDMR was working on hepatocytes. They were talking about, they were doing some chemical experiments where they were insulting the hepatocytes, and then they were trying to see what was the change. So that way we can do it, but we should know that how the experiment will work. Electron microscopy, where we can combine these antigens can be targeted and you can combine it with the gold part. There is a different methods that can be. But yes, because it is a very technical thing, so you will have to see what is the best protocol that can be. It's time. Yes. You have a particular answer. Yes, it is. Pituitary adenomas. You have dense granules. You've heard about dense granules? Yes. So they are dense granules and sparse granules. So there is a role of electron microscopy. That is how you say they are dense or sparse. Pituitary adenomas. But as I said, it's a hypothetical answer in the way that no one will process a pituitary adenoma to look for sparse granules and dense granules, because now you have histochemical markers which can differentiate whether it is a dense granule or a sparse. And you have to realize that the amount of tissue that you are looking at in an electron microscope is very small. Not so small as it appears at one time we even see 3, 4, 5 lambda in the same section, but otherwise it is small relatively. So if you see a small area and say this is just sparse granules, these are just dense granules, that will not be right. Anyone from gastro? Surgical gastro, so there is gastroenterology. Surgical gastro, do you remember anything? Once we have surgical gastro, you don't see gastroenterology. No endoscopy. Okay. There are some infections in gastroenterology where electron microscopy is very important. It cannot be looked by in a light microscope. Okay. Any other questions or even questions from the last 2 classes? So how did you like this microscopy course, or yes, you are just doing it for you want? We'll talk about operative microscopy tomorrow. Maybe people will be interested. Okay. That is what I talked about. I told you that the tissue is taken on a grid, a very small grid. I showed you a grid, no? It is such a small grid that is just 3 millimeter. That is what can go inside. Right? This is the grid which can go. A slide will be something like this. Right? So nothing can go inside. And of course, as I said, glass cannot go inside. For example, if you want to put a technology specimen, particulate matter, or sunlight, you can embed it in agar, and then it will be like a tissue now, and you can cut it. Okay, so we can break if the, I think refreshments will be there because Dr. Mitra is already there, so he'll start at sharp at 4. So this is the specimen chamber. So here is the grid which goes. That is what I'm trying to show. So there is no space for a larger